All right, so here we're on 12.4 on the definite integral. Here we're going to approximate areas by left and right sums. We're going to look at the definite integral as a limit of sums, and we're going to look at the properties of definite integrals. All right, so the definite integral is used to compute areas, such as we have, the area under this curve. We want to know what is the area of that shaded region. Probabilities, average values of functions, future values of continuous income streams, and many other quantities. So again, we can use the definite integral to figure out the area under this curve, and we'll see that here in a little bit. First, though, we're going to look at approximating areas by left and right sums. Now, how do we find the shaded area in figure 1? Well, that is, how do we find the area bounded by the graph of the 0.25x squared plus 1, the x-axis, which is at the bottom, and the vertical lines where we said from 1 to 5, okay? Now, the formula for the area of a rectangle can be used indirectly to do this. And to see how we're going to do that, we're going to look at the method of approximating the area under the graph by using rectangles, which is what we kind of see here down in the bottom corner. We're going to use rectangles to kind of calculate the area. Now, this method will give us any accuracy desired, which is quite different from finding the exact area. Now, our first area approximation is going to be made by dividing the interval 1 to 5 by 4 equal parts. So if we look, we have 4 different pieces. So we have 4 rectangles, okay? And how we find that is we take our endpoints, 5 minus 1 divided by 4. So each one of these is going to be 1 unit basically across. Then we place a left rectangle on each subinterval. That is a rectangle whose base is the subinterval and whose height is the value of the function at the left endpoint of the subinterval. So what that means is we're going to start down here at 1, and we're going to go up until we hit the graph, and then we'll move over until we get to the point where the next interval starts. And then we'll have a vertical line to that. And basically, you're going to draw all these vertical lines to the graph. And then we're just going to kind of, at that graph, we're going to do a line across, we're going to do a line across, we're going to do a line across, and we're going to do a line across, and then we have to go down here on this one. We didn't draw a line up there. And so that's what we're going to do is we're going to find the area of each of those 4 rectangles. Okay. Now this is, again, the left rectangles. We'll do right rectangles here in a little bit. So what we have is, what is the width? Well, the width is 1. Now we have to figure out the height. Well, the height's going to be when we plug in 1 into this function, that's going to give us this value. When we plug in 2, that's going to give us this value. When we plug in 3, we'll get that value. When we plug in 4, we'll get that value. And once we have those, that's going to give us what f of 1, f of 2, f of 3, f of 4 are. And that's going to be basically 1.25, 2, 3.25, and 5, because each one of those is just 1 for the areas. So when you multiply them, you just get out whatever that height is. Then you add them all together, and that tells us the area is 11.5 using left rectangles with, 4 subintervals here, okay? All right, so we can see that, f of x is increasing. We see that the left sum underestimates, because if you look at that, we're missing quite a bit of area. We're missing all this area here, all this area here, all this area here, and, all of that area there. So what we know then is 11.5 is equal to L4, but that's less than that total area. So now what we're going to do is we're going to do the right endpoint of each subinterval to find the height of the right rectangle. And then we're going to figure out the areas there. So again, now we're going to the right. So we don't do the first interval, we do the second piece. So we go up and we hit the line, then we draw an arrow across and then down to our first one. We go up till we hit that, draw an arrow across and down. And we just keep doing that. And this time you notice we're going up here and over. Now what we can see is these are overestimating the areas. So these are going to give us an area that's greater than by about that much and about that much and that much and that much, okay? And so that's kind of what this is saying here. Again, we're going to calculate what the areas are. And so we have to do, in this case, we're doing f of 2, f of 3, f of 4, and f of 5 to get that. And again, it's a width of 1, so we just find that, and we find that it's 2, 3.25, 5, 7.25. Add all those together, we get 17.5. And so what that says is the max we see here with 4 subintervals is 17.5, whereas the min we saw was 11.5. We underestimated it here, and we're overestimating it here. So what basically that's saying is our left rectangles is less than the area, but that's less than the right triangles, which is, equal to that. So we're somewhere in that range. So that's kind of the key, is we're in between. We're not exactly at the right value. Now, as we can see, that first is fairly coarse, from 11 to 17. That's quite a distance. So what we could do is we could actually go into more subdivisions. In this case, what they're showing in this picture in figure 4 is 16 subdivisions. And so then what you're going to do is you're going to have to do all of them. Now, each one of them is going to be a quarter distance apart. So instead of, 1, it's going to be the quarter. And so we're going to have to multiply by 0.25. But we're still going to find, depending on if it's the right or the left, if it's the left one, we'll find that point and then times the 0.25. And if it's the right one, we'll find that one for this way. And so we're going to have to do that for all those. It's hard to see on here. That's why I went back to the other one. But that's what we're going to be doing on all those points. And so we'll add them all up. We skip a lot because there's a lot there. And we find it goes from 13.59 to 15.09. So then we know between the left and right areas, it's going to be somewhere between that, and that is the actual true area. Now, if we wanted to, we could also go even more. We get to 100 subdivisions. Then we're going to be between 14.214 and 14.454. So we're getting better and better all the time. The more subdivisions we do, the closer to the actual value of the area under that curve we're going to find. Now, the error in an approximation is the absolute value of the difference between the approximation and the actual value. So in general, neither the actual value nor the error in approximation is known. However, it's possible to calculate an error bound. Okay, that's a positive number such that the error is guaranteed to be less than or equal to that number. So the error in approximation of the area under the graph from 1 to 5 here, by the left sum, L16, or the right sum, R16, is less than the sum of the areas of that small rectangles in figure 4 by stacking them up. So we're stacking all those rectangles up, and it's going to be less than that. So our error is absolute value of area minus L16, which is going to be less than f of 5 minus f of 1 times the delta x, and that's going to give us a 1.5. Okay, so doing the calculation, we find that out. And therefore, 1.5 is the error bound for approximation of the area f by L16. And we can apply the same stacking argument to any positive function that's increasing on the closed interval from a to b, so 1 to 5 or 2 to 3 or whatever it is. And we can obtain the error bound in theorem 1, which we'll see here on the next page. So they're going to ask, what is the error bound for approximations of an area by a left or right sum? So again, if our function is greater than 0 and is either increasing on a to b or decreasing on a to b, then f of b minus f of a, the absolute value of that difference, times b minus a divided by n is going to be an error bound for the approximation of the area between the graph of f and the x-axis. Now that's going to be from x equals a to x equals b by either a ln or an rn rectangles. Now the limit of left and right sums. Well, if f of x is greater than 0 and is either increasing on a to b or decreasing on a to b, then its left and right sums approach the same real number as n approaches infinity. So that's the key. As long as we get close to infinity, it's going to approach the same value as we go. Okay, so but we're not going to be able to break them down infinitely amount. And so what we'll do is we'll do something else. So let's pause there and we'll come back with an example.